Okay, I think we're recording. We'll find out. So the very first thing I wanted to do was to talk. We're going to go back to some very fundamentals of soil mechanics, and I want to talk about this concept of state variables versus material variables. And I'm going to get into just a little bit of unsaturated soil mechanics. We're not going to do unsaturated soil mechanics in this class. But I've come to the conclusion that we should be getting there eventually, and so I'm going to talk a little. There's 2 or 3 times we're going to talk about some characteristics of unsaturated soil. You know, in practice we don't do this too much unless you're in that specialty. But you know, the more and more we are learning about this, I think the more and more I've come to the conclusion we should really approach this stuff fundamentally. That the saturated soils are actually, you know, a small subset of the world. But we're not really going to be doing, I'm not really going to be doing unsaturated soil mechanics, but I'm going to talk about it a little bit. So there'll be some hand waving because we're not really going to get into it. But I think some of the concepts in there will be important for us. So so for this module, these are the learning objectives for this module. This is a very short one. Oh, and when you look at the modules, there's a 1.1.1 and a 1.1.3, and there's not a 1.1.2. That's because I thought I was going to break this thing into 2 pieces, and when I got down, I said, nah, that's too short to do 2 pieces. So there is no 1.1.2. You're not missing anything. I just did the older ones first and came back to do the early ones and then decided I didn't need one. So the big deal here is I want you to understand the difference between state variables and material properties. And that's not going to mean anything to you right now, but hopefully in about 10 or 15 minutes it will. And we are going to talk a little bit about saturated and unsaturated. I won't really theoretically, I won't get into the theoretical basis for all the unsaturated material. And this is mostly going to be stuff that you've already seen once, but it's a different way to look at it and it's a different vocabulary. So state variables versus material property variables. So a state variable is a non-material variable required to describe a certain behavior or of a material under consideration. That's nice. I pulled that straight out of a textbook. But let's contrast that with a material variable. And the big point is it has to be independent of material properties. So if I can put 2 different kinds of soil under the same state, or I can put 2 different, I'm going to show you water. I can have 2 different places where 2 different water could be in the same state, or one could be water and one could be oil. So the material properties would be different, but they'd be in the same condition. They'd be under the same state. So these are properties that are independent of the material properties themselves. Whereas the material properties are obviously properties of the material. Material properties link the condition that the material is under the state to its behavior, but the state is independent of the materials. So, for instance, if I was pouring oil out of a pitcher and I'm pouring water out of a pitcher, if I got the same size pitcher, I'm holding at the same elevation, I'm pouring them out. They're both under the same state. They're both at the same elevation. The hole in the pitcher is the same size, but they're going to come out different because they have different material properties. But the state, that elevation that they're at, and the size of the hole in the thing, and the angle that I'm holding out, that's all going to be the same. But the behavior is going to be different because the material properties are different. And I'm going to give you some specific examples here. The other thing I'll say about the state is it's related directly to a particular material behavior. So the state that water is under in terms of how it's going to flow is going to be different than the state that you would talk about if you're talking about how temperature is going to flow through it. They're different states. So the state is directly related to a behavior that you're interested in, and it's almost always related to a specific model of the material properties are always related to a specific model that you're doing, because there's different. We have different models for the way that things behave. The property is going to be important to the model that we're using. I think I just said this one. This is what links. It's the material properties that link a state to a behavior. All right, so here's a couple examples that I hope will make that theoretical discussion more clear. So the first one we'll look at is just incompressible flow of water. So this is something you all know. What drives the flow of water? It's change in total head, right? We learned this right? It's change in total. It's not change in elevation head. It's not change in pressure head. It's not change in velocity. It's change in total head. That's what drives flow of water in pipes. That's what drives flow of water in soils. That's what drives flow of water in open channel flow. That is the state variable. Notice that I'm not saying anything about, in fact, this is for any kind of incompressible flow. This could be oil. This could be water at a certain temperature. This could be water at 30 degrees Celsius. It could be water at 160 degrees Celsius. What's going to drive its flow is all going to be driven by the total head. Change in total head drives flow. We've expanded that out. Remember, the total head is equal to the elevation head, which is just Z, times the pressure head, which is the pressure divided by the density of the fluid, plus the velocity squared divided by 2g. We know that. And then Bernoulli's equation is the equation we use. You all remember Bernoulli's equation? Bernoulli's equation just says if I have the total head at one point, so that's going to be Z1, P1. So this represents, whoops, this is what I wanted to do, pin. This represents the total head at one point. Then that's got to be equal to the total head at another point, point 2, plus whatever losses there are between the two. And we got all kinds of models for the losses. Okay? So that's something we all know. So, whoops, how do I tell this thing then not to? So what are the material properties? So the state variable is the total head. This is our model, right? This is our model right here that we're going to use. We're going to use Bernoulli's equation as a model. What are the material properties in that model that are going to be important to the water's behavior? Okay, density is one, and there's another one which you probably know. It's hidden in here, and it has to do with the frictional losses. So besides density, there's one. What do we know when we're doing on the frictional loss? The viscosity. Yeah, the related to friction. So the two. So that's it. You got it. So the two properties are the density rho and the kinematic. Well, you could use the kinematic or the true viscosity, however you want to do it. But the viscosity. So notice this. That the state variable is head. Doesn't say anything about the condition of the fluid. Doesn't say what kind of fluid it is. Doesn't say anything about the condition of fluid. And notice that in the properties that we're interested to describe the behavior, in which case the behavior is flow, are the density and the kinematic viscosity. Notice that those are related to the model. If we were interested in a different behavior of the water, we would have a different model, we would have different material properties. And we would have a different state variable too. So both the state variable and the material properties are related to the behavior that you're interested in and the model. Okay. And then I'll do one more, which gets closer to what we're going to talk about. Can I do this? No, that's not going to work. I was hoping to erase my boo-boo there, but I guess it's not going to work. We're going to talk about stress and strain in soils. Well, let's take a really simple one. Let's just talk about a bar and tension. Okay, so what's my state variable for this bar and tension? This should be pretty easy. I got a bar, I'm pulling on it. What's the condition it's under? Yeah, the tension, and how do we describe that? How do we describe the magnitude, the amount of tension in it? Okay, it's either T, it's either the force, or we more commonly, we stress. In this case, there's only one stress, it's a normal stress. That's the state variable. That could be aluminum, could be steel, could be wood, could be concrete, be kind of tough, probably not soil. But I'm not saying anything about what the material is. I could have a whole bunch of different materials in tension, bars in tension, under that state. And they're going to behave differently, but they're still all under the same state. They got a tension of T on them with a certain cross-sectional area is going to give them a certain normal stress. Okay, so the model we're going to use, if we're interested in this deformation, is Hooke's law, right? So that's simple. I'm going to give it to you in two pieces, actually. There's two pieces of this one. Okay, so the simple one is the change in length. We'll just do this as a change in length. Change in length is equal to the original length times the stress divided by Young's modulus in this case, right? That accounts for the boundary conditions, right? But what if I ask you about how much it's going to shrink? When I pull, it's not only going to elongate, it's going to shrink in diameter, right? So what's that equation? And that's another piece of Hooke's law. Yeah, so it's Poisson's, the Poisson's effect. So the change in the radius is going to be equal to the original radius times the Poisson's ratio times the normal stress divided, right? So this is easy. What are my material properties in this one? Poisson's ratio and the Young's modulus. Right, see, that's easy. It's going to get harder, so we do the easy ones first. Okay, so the material properties are Young's modulus and Poisson's ratio. Very, very simple. Okay, let's talk about a more complicated one. So if I'm talking about, now, when we do soils, we're doing continuum mechanics. We don't have beams, we don't have bars, we don't have wires in soil, we have continuum, right? We're always dealing with our simplest model of soil is an elastic half space. It's a half space because it only covers half of the entire world, and it goes down forever and above its air, so it's a half space. And so we need to be able to look at elemental areas. So what are the state variables for this? Without talking about what this material is, if I want to look at a piece of a big body of material and I've taken out, I could put dx by dy by dz on this. I could put, this is going to be, let's see, this one's going to be dx. This would be dz in this direction, and this would be dy in that direction. So I've got an elemental area. If I'm concerned about its mechanical behavior, its deformation, what's the state that the condition it's under? Without talking anything about the material, how do I describe the state it's under? What are the things that are going to happen to it that cause it to deform? Stresses, right? And how many stresses am I going to have in this case? I'm going to have 3 stresses on, I'm going to have a total of 9 different stresses, right? I'm going to have normal stresses and shear stresses on each surface. So, and we're going to talk in just a minute. We're going to talk about tensors and how we write those things. But I'm not going to talk about the material variables in this because that depends a lot on models, and we're not going to talk about that right now. But those are the state variables for the mechanical behavior of a continuum material, for a solid material. Those are the state variables. Those ones we're going to talk about a lot in this class. All right, so let's look at soil and talk very briefly about what the soil looks like and how we might characterize its state variables. So we all know this. So soil is a 3-phase material, and it's got solids, water, and air, right? Or if we want to get really general about it, it's got solid material, it's got gas, and it's got liquids, because we have to deal with soil that's got gasoline in it and all kinds of other things. But we're just going to stick with the simple one right now. And sometimes the gas is not air, but that's what we're going to stick with right now. And we all know this model that we use to talk about just the quantities of those materials within a volume of soil. All right, well, let's consider, let's go back to a 1D thing just to make life easy for us. And let's consider that the behavior we're interested in this soil is 1D compression, and we're going to do a saturated soil. So all we have is solids and water. Okay? So what is our state variable for this one? We all know this. What's the state variable for this? We're not even talking about, we're only going to talk about the state variables. We're not even going to talk about the material properties in this. We'll get to that later. So what controls how much a saturated soil compresses in 1D? What's the controlling variable? Yeah, it's not just any normal force. Which normal force is it? There's a very what's the most important equation in all of soil mechanics for these that ever took it from me? Tutsagi's concept of, it has to do with it being a 3-phase material. Right, and it's related to pore pressure. What stress is going to control how much this thing compresses? The effective stress, right? That's our state variable. Our state variable is the effective stress. Now, there's 2 ways to say that. You could either say that our state variable is the total stress and the pore pressure, but the behavior in this case is really not dependent on the total stress and pore pressure. The behavior is really dependent on the effective stress. So for this one behavior, only for saturated, notice this is only appropriate for saturated soil. And we're talking about 1D compression, so we're only talking about one stress. The state variable is the effective stress. All right, well, let's go back to our unsaturated soil now. Now, what's going on in our unsaturated soil? This is where I'm going to wave my hands over a bunch of unsaturated soil mechanics, but we'll talk about it conceptually. I think they're all things that if you don't know, I think you'll understand. Well, we have, in our water is under some pressure. Now, when we talk about a pore, now our pores now are of two-phase material. They have water and air in them. Well, the water's under some pressure. It has, it has a state variable, if you want to think about that. It's the water pressure. And the air has a pressure too, and they're not the same. And we've got to actually use thermodynamics to understand the relationship between those two. So we've got, in this case, we've got water pressure and we've got air pressure that aren't the same. So when the saturated one, all we have is water pressure. The same way we say pore pressure, we mean water pressure. So when you talk to unsaturated guys, they never use those words because there's two different ones in there. The other thing that's going on is we have these menisci forming in there. This is called the water-air interface, or the tensile membrane, that's causing the. This is actually a behavior. This is not a state issue, but it's a phenomenon that occurs. And what's the sign of the? If I measure the pore pressure here inside this little place where there's a little bit of water and there's a meniscus forming there, compared to atmospheric pressure, what's that pressure going to be? It's going to be negative, right? That's capillary action. It's going to suck, just same reason, when you drop your paper towel on a spill, that it sucks it in. Same thing. So that's actually going to have a negative value, that pore water pressure in there. So if we look at, so I just drew this little elemental area. So if we're looking at the behavior, and let's say we really, and we understand, we're going to talk about this more later, but we understand that the real behavior of the deformation of the soil skeleton is really driven by the effective stresses, which is that contact stress conceptually. Not really a contact stress, but conceptually it is. Well, what's going on here? Well, we've got the air pressure pushing this bubble out, and we've got a negative pore water pressure. So I've got three different stresses going on there, two pressures and one stress going on, and these are all related to the mechanical behavior of the soil for unsaturated soil. But I don't really have, I've got these three, I call them stress values here, actually two of them are pressures, but I've got these three values, but because of the interrelationship between them, this is where I'm not going to explain this too much, there's really only two possible independent state variables I can have. I can't have three because of the interrelationship between these three. So because this has to do with, because it's a two-phase material, the water, the pore part is a two-phase material. It's a three-phase material altogether, but the pore part's a two-phase material. So what are my choices? Well, it's the differences in these. So I've got three choices that I can do. I can either have the two state variables be the total stress minus the air pressure, and the air pressure minus the water pressure, the difference between those two. Or I can have them be the total stress minus the water pressure and the air pressure minus the water pressure, which is the one you might think we use, because that first term, this first term right here then is what to us traditionally. That's our traditional effective stress, but in unsaturated soil mechanics, that's not correct. Or we could use this third definition, which is the total stress minus the air pressure and the total stress minus the water pressure. The one that's generally used, these have all been used at different times in unsaturated soil mechanics, but by far the one that's used most commonly now is this, which may not seem sensible at first, but it's the total stress minus the water pressure and minus the air pressure, and the air pressure minus the water pressure. And it turns out when it becomes saturated, the definition becomes consistent with effective stress, because then the air pressure is zero, and the difference between the air pressure and the water pressure is zero, and then you have the same that the effective stress is just equal to the total stress minus the pore water pressure. So I don't do this to get you all excited about unsaturated soil mechanics, but I just want to point out that this is a complicated material. But we can still, even in this complementary material, we can define the state variables. So notice that these two state variables, the total stress minus the air pressure and the air pressure minus the water pressure, I don't say anything about how saturated the soil is, whether it's a clay or whether it's a sand, or anything about the material. I've not said anything about the material. This is the state that it can be in. And then you can do this in 3 dimensions. We're just doing it in 1 dimension right now. So that's a state variable. It's about the condition under which the material is in without saying anything in particular about the material. I mean, we have to say that we have to describe the behavior we're interested in. In this case, we're interested in the mechanical. This is 1D compression we were talking about, right? We're interested in the mechanical behavior of it. So we have to say that much about it. But we're not talking anything about what that material, the properties of that material specifically are. And I believe that's the end of the state variable one. Oh yeah, so quick summary. So state variables describe material behavior independent of the material properties. They don't maybe that first one I should rewrite. They describe a condition that is important to the material behavior. So let me edit that. So they're describing a condition that will drive material behavior, but it's independent of the material properties. So for soils, if they're saturated or completely dry, then our state variables are either the pore pressure and the total stress, or we can write the effective stress, because that's the one that's really important, right? And for unsaturated soils, there are these two state variables: total stress minus air pressure, and air pressure minus water pressure. All right, questions about state conditions? Because that's a little philosophical, but it's going to be really important as we get into our next set of things. And at that note, it's 7 till. So let's take 7 minutes, and I will attempt to see if my recording is working.